let's be real for a sec. Physics, it can feel like you're wrestling with a whole new language, right?
It can be a little intimidating sometimes.
Totally. But what if I told you that getting how things move, like literally everything around us, boils down to a few key ideas?
It's true.
That's our deep dive today.
Yeah.
We're tackling IGCSE physics, focusing on motion and forces. We're talking about those formulas you've probably seen, like speed, acceleration, and figuring out how to actually make sense of them. No need for a PhD here. We're breaking it down, especially for new students.
And the best part is that these concepts, they're not just some abstract theories. They're literally happening all around us constantly.
Exactly.
Yeah.
So let's start by visualizing movement. Like imagine a GPS tracker,
Yeah.
but for any object. That's where these things called distance-time graphs come in.
They're super useful.
Right. So picture this. Plotting your own trip to school on a graph, that's essentially what a distance-time graph is doing.
Yeah, it's like a map, but instead of showing streets and buildings, it shows an object's journey through time. And the best part is these graphs, they unlock some pretty cool secrets about an object's speed, and you don't even have to do a million calculations to figure it out.
Okay, so tell me more about this secret speed code hidden in these graphs.
Okay, so picture this. A steep line on the graph. That means the object is moving fast, like when you're racing downhill on your bike.
Okay.
A less steep line, that means it's moving slower, maybe like a leisurely stroll through the park.
Gotcha.
And a flat line, that's like hitting the pause button. The object is standing still.
So the steeper the line on a distance-time graph, the faster that object's moving.
Yeah.
That makes sense.
Yeah.
But how do we actually put a number on that speed? Like, if we see a steep line, how do we figure out exactly how fast that object is zipping along?
That's where the formula for speed comes in. And don't worry, it's way less intimidating than it sounds. Speed is simply the distance something travels over a certain amount of time. Think about it like this. If you drive 60 miles in 1 hour, you're averaging a speed of 60 miles per hour.
60 miles in 1 hour, 60 miles per hour. Got it. So it's just distance divided by time.
You got it. And to make it even easier, we can actually just use the gradient of the line on the distance time graph,
Okay.
which basically tells us how steep the line is, like finding the slope of a hill, right?
Right.
And guess what? That gradient is actually the speed.
Oh, wow.
We usually write this as speed equals delta y over delta x, or speed equals triangle y over triangle x,
Okay.
which just means the change in the vertical distance divided by the change in the horizontal distance.
Okay, so we can actually see the speed right there on the graph just by looking at how steep the line is. And if we want a number, we use that formula, speed equals distance divided by time.
Exactly. It all connects. And here's where it gets really cool. This formula isn't just for graphs. It works for any situation where you're trying to figure out speed.
So if I'm trying to calculate the average speed of like a snail racing across the garden, I can use that same formula, distance divided by time.
You got it. Though I have a feeling that snail's distance time graph might be a little less dramatic than, say, a rocket launch.
Definitely a less steep line on that graph. Okay, so we've cracked the code on distance time graphs and speed.
Yeah.
But what about like in real life when speed isn't constant? You know, like things are always speeding up or slowing down.
Right. That's where acceleration comes in. And it's not just about going faster. It's about how quickly your speed is actually changing.
Okay, so give me an example. When would I feel acceleration?
Okay, imagine you're on a roller coaster, right? And you get that feeling of being pushed back in your seat as the ride takes off.
Yeah.
That's acceleration. Or think about slamming on the brakes in a car.
Yeah.
You're changing speed super quickly, which means you're experiencing acceleration just in the opposite direction. We call that deceleration.
So acceleration is like the thrill factor of physics.
Yeah.
It's all about those changes in speed. But how do we actually measure that? Is there a magic formula for acceleration too?
There is. And just like with speed, it all comes back to distance and time, but with a little twist. Acceleration is the change in velocity over a certain amount of time.
Hold on, velocity. I thought we were talking about speed. Are those different?
Yeah, you're right to point that out. Velocity is basically speed, but with a direction. So if you're driving 60 miles per hour north, that's your velocity. If you're driving 60 miles per hour south, it's the same speed, but a different velocity.
Got it. So acceleration cares about which way you're going, not just how fast.
Yeah.
But back to the formula.
Right. So since acceleration is the change in velocity over time, the formula is acceleration equals delta v, which is the change in velocity over t, which is time. We write that as a equals delta v over t. So if you go from 0 to 60 miles per hour in 5 seconds, you're accelerating at 12 miles per hour each second.
Whoa, that's some serious acceleration.
Yeah,
So just like with speed, we can see acceleration on a graph too, right?
exactly. We use something called a velocity time graph. And similar to distance-time graphs, the steeper the line, the greater the acceleration. A flat line means the object is moving at a constant velocity. No acceleration is happening.
It's all coming together. So a steep line on a distance time graph means high speed, and a steep line on a velocity time graph means high acceleration.
You got it. And just like the area under a speed time graph represents the distance traveled, the area under a velocity time graph also tells us something important, the displacement.
Displacement. Is that just another word for distance?
It's similar, but there's a subtle difference. Distance is the total length of the path traveled, while displacement is the overall change in position from the starting point to the ending point. So let's say you walked all the way around your block, ending up right back where you started. You've covered a certain distance for sure, but your displacement is actually 0 because you're back at your starting point.
Okay, that makes sense. So if I wanted to calculate the displacement from a velocity time graph, how would I do that?
Just like with the distance time graph, you calculate the area under the velocity time graph. If it's a rectangle, you just multiply the base by the height. If it's a triangle, you multiply half the base by the height.
It's like geometry class just got way more interesting. So we could use these formulas and graphs to like break down the movement of anything from snails to spaceships.
Exactly. And the more we understand these basic principles, the more amazing the universe becomes.
Okay, so we've covered a lot of ground here. Distance, speed, acceleration, even displacement.
Yeah.
But it all seems, I don't know, a bit theoretical. How does understanding all this stuff actually play out in, like, the real world?
Well, imagine yourself driving a car.
Yeah.
You're cruising along, not a care in the world. And suddenly, bam, a squirrel darts out into the road.
No, poor squirrel. I hope you slammed on the brakes.
Exactly. And that right there is a perfect example of physics in action.
Okay.
That distance your car travels from the moment you see the squirrel to the moment you actually hit the brakes.
Yeah.
That's called your thinking distance.
So it's all about reaction time, like how long it takes my brain to process squirrel and tell my foot to hit the brakes.
You got it. And a lot of things can actually affect your reaction time, like being tired or distractions like your phone, or even how much coffee you've had that day.
Yeah, that makes a lot of sense. So thinking distance is all about what happens before you even touch the brakes. But then there's that like heart-stopping moment when you're actually trying to come to a stop.
Right. And that distance your car travels once you hit the brakes, that's called your braking distance.
So thinking distance plus braking distance equals the total distance it takes to stop the car. That makes sense. But what about braking distance? What affects that?
Well, think about driving on a rainy day. The roads are wet, maybe a little slippery. Do you think you'd need more or less distance to stop compared to a dry, sunny day?
Definitely more.
Right.
It's way harder to stop on a slippery surface.
Exactly. So road conditions play a huge role in braking distance. And here's the physics tie-in. A wet road has less friction, which is that force that helps you slow your car down. Less friction means you need more distance to stop.
So it's all about friction. What else affects braking distance?
Well, speed is a big one. Think about it. The faster you're going, the longer it's going to take to stop. That's why we have speed limits. They're actually designed with braking distance in mind.
Oh, that makes sense. And I'm guessing the condition of your car matters too, right? Like if your brakes are worn out,
Yeah.
that can't be good.
You're right. The condition of your brakes, your tires, even how much weight is in your car, all of that can affect how quickly you can stop.
Wow, so something as simple as understanding speed and braking distance can actually help you stay safe on the road. That's pretty cool.
It is. And it all comes down to those fundamental physics concepts we've been talking about. Distance, time, speed, even forces like friction.
This has been an amazing deep dive. We've gone from like deciphering those sometimes scary formulas to seeing how physics actually plays out in everyday life. Who knew physics could be so relevant?
And even kind of fun, right?
Definitely. We've learned how to read the story of motion hidden in graphs. We've decoded the language of speed and acceleration, and we've even uncovered the physics behind safe driving. But here's the best part. This is just the beginning.
There's a whole universe of fascinating physics out there waiting to be explored.
So true. So keep those physics brains fired up, and we'll catch you in our next deep dive.